So now coming to the sinusoidal signal, in continuous time domain x of t is a sine of omega t plus pi, where a is amplitude, omega is angular frequency in radians, and pi is phase angle in radians. Right. Okay. And the waveform is mentioned there, and you observe the pi angle there. Okay. That is the phase shift from 0 to the time at which it is starting from 0 magnitude. Okay. And the time period is, you know, that equals to 2 pi by omega, and in discrete time it is x of n equals to a sine of omega n plus pi. That means only t is getting replaced by small n. And here if you observe, the time period in discrete time will be 2 pi by omega into m. Okay, we'll come to know about this m in periodic signals and all. Right. Okay. So all continuous time sinusoidal signals are periodic. Okay, all continuous time sinusoidal signals are periodic, but discrete time sinusoidal sequences may or may not be periodic, depending on the value of omega. Okay, remember this. And similarly, for a discrete signal to be periodic, the angular frequency omega must be a rational multiple of pi. That is the condition for a discrete time sinusoidal signal to become periodic. That means for a discrete signal to be periodic, the angular frequency omega must be a rational multiple of 2 pi. Okay. And next one important function is rectangular pulse function. So it is defined like this, denoted by pi of t by tau equals to 1 for modulus t less than tau by 2, and it is 0 otherwise. So what is meant by this modulus t less than tau by 2? That means the rectangular pulse is existing between minus tau by 2 to plus tau by 2. The total length of time will be tau. Okay, that's what mentioned in the in this pi of t by tau. So whatever is there divided by that means whatever is there in the denominator is the total length of the pulse. Total length, not half of the length. Right. That is very important. There are two important functions are Signum function and Sinc function. Okay, in case of Signum function, it is defined as Signum of t equals to 1 for t greater than 0 and minus 1 for t less than 0. Right. Then what is the value at t equals to 0? And you can easily observe that at t equals to 0, is it continuous or discontinuous? It is discontinuous, because at t equals to 0 plus the value is plus 1, at t equals to 0 minus the value is minus 1. So as they are not equal, they are discontinuous. I think everyone know how to find out whether a given function is continuous or not. That means you need to consider 0 plus and 0 minus, and if they are equal, that is continuous, otherwise discontinuous. So here this signum is discontinuous at 0. Then what is the value at 0? It will be average of both of them, that is plus 1 minus 1 divided by 2. You will get 0. Right. Okay. And you can represent in terms of unit step this signum function as equals to minus 1 plus 2 into u of t. There are other ways of representing this signum in unit step that you will come to know in the problems. Okay, so then comes sinc function. So this sinc function is defined as sin t by t for all t, that is minus infinity to plus infinity, and the waveform is represented like this, and it oscillates with a period of 2 pi and it decays with increasing time t. So from the figure you will come to know that. So its value is 0 at n pi, where n is plus or minus 1, plus or minus 2, and so on. Okay, and it is an even function of time because sinc of t equals to sinc of minus t, right? Okay, thank you.